You doing all right? Cool. And I know that we've been through some maybe stuff that you're maybe have not seen as much, a little bit less familiar with limits. The good news is this is the day when we start pulling ourselves out of the limits. So the goal for today is to get out of the limits. So we're not going to get out of it completely, and you definitely need to know limits for the exam. But I don't want you to think like all mathematicians do all day is just sit around and take limits. There's so much more fun things we get to do. Let's start with our problem. Consider the following function. It's a piecewise function. If you're below 0, you look like x squared plus 1. If you're between 0 and 1, you look like x squared plus x. If you're above 1, you look like 3x minus 1. And then there's a series of 5 statements that says, which one of the following statements is true? So one of these things is true. And they deal with the questions of being continuous, not continuous, differentiable, not differentiable, at the points 0 and 1. Now, why does it focus on 0 and 1? Well, away from 0 and 1, these are nice functions. They're polynomials. So we don't have any problems except where we try to glue. Now, if our problem is continuity, it's not continuous if this is happening, where they're coming together and there's a gap. That's bad. But, okay, so maybe it's continuous. That means they come together. But does that mean it's going to be differentiable? Well, no, because you don't want this. You don't want them to come together, but there's sort of a definite kink, kind of like an absolute value function. You want things to line up. All right, so A, B, C, D, or E. What's the answer? Did anybody get the answer to this one? I see a hand back there. Is it D? Is it D? Yes, it is D. It is not continuous at 0, because as you come in from the left and the right, you get different answers. Now, as soon as you know it's not continuous, you don't even bother with differentiable, because if you're not continuous, you're not differentiable. At 1, we are continuous because from the left and the right, we get the same answer. So it's continuous, but we still have to go a little bit further. We have to say, well, is it differentiable? So for that, we say, okay, how do you know if something's differentiable? Look at the derivatives. Now, I'm not being fancy and taking very complicated derivatives here. I just say, well, look, I know how to take derivatives of the pieces. Derivative of x squared plus x is 2x plus 1. Derivative of 3x minus 1 is 3. Take the limits of those pieces, and they match, which means they come in nicely. It looks smooth. So it is differentiable. All right, so D is the correct answer. Good. Nice. All right. We're ready. If we see a problem like that again, we'll know how to answer it. So, continue with our problem solving. We're on step 3. Let's recall. What was step 1? If I want to solve a problem, what's the first thing I need to do? You got to understand it. You can't solve a problem if you don't know what it's asking. Okay, then we said, okay, I understand my problem. What was my next step? Create a plan. I need to think about what I'm going to do. That brings us to the third step, which is we should probably do something. So this is the doing, the solving. Carry out the plan. And here, this is not so much the hard part, but there's some things that you should keep in mind. Can you check each step? So one of the things you want to learn is to get into the habit of saying, you know, I want to catch my errors. I don't want the graders to catch my errors, because then I'll lose points. I'll catch my own errors, and then they won't catch them, and I'll get all the points. Got to get them all. Got to get them all. Okay, so check your work. Catch your small mistakes. Can you follow your solution? And in particular, is it organized? I do think that my experience has been, and that when I look at a solution, if I can easily follow the flow, that person tends to score higher. Maybe it's because it's easier for me to see where they did things right, but I think it's also because it's easier for them to see where they did things wrong. So when you're writing, think about how to organize your work. Because you want to go through and think about, okay, what's happening? And if you get stuck at a step, you want to be able to go back. Sometimes we get solutions and we look at it and we just can't figure out the flow of thoughts because it just seems like they were randomly writing things over the page, and like every 30 seconds they were rotating the page like 15 degrees. So it's just at all sorts of strange angles. So be kind to your graders. Be kind to yourself. Be organized. And also be open to adjustments. We always have a plan. Doesn't mean that things will happen like we think. And you might get into it and you say, oh, something interesting has popped up, something unexpected. So be ready to adjust your plan because there might be something even better than what you originally thought. All right. So come back next time to find out what the last step is. Oh, what could it be? So, all right. What's the goal for today? We've been talking about derivatives, but so far when we talk about derivatives, we've talked about this sort of notion of, oh, there's this limit definition. A limit is h goes to 0, f of x plus h minus f of x over h. But hopefully you're becoming convinced that seems inefficient and time-consuming. And you're right, it is. It's not a very good way to do things in general. Sometimes you have to do it, but in general, it's actually very hard to do it on every problem. So what we want to do is we want to say, well, let's figure out a better way. The way I like to phrase it is we want a nicer user interface. Because derivatives are great. They give us information about how things change. And we can use information about how things change to answer questions. But we need to be able to do the derivatives. So we start saying, well, what can we do? Well, what we'll do is we'll go back to our definition and find some rules. And we're going to use these rules to help us, to make it simpler for us to take derivatives. And there's two categories for the rules. The category number one is we need to know some basic functions. All right, so we're going to start with those. There's some over here. But I also want to add that there's a second category, which is how do we put things together? So if you've ever played with, say, Lego before, you have a whole bunch of different building blocks. But just because you have the blocks isn't enough. You also have to know how to put the blocks together to form your answer. So you need both pieces, the way to either the building blocks and the way to put them together. So today we're going to do 3 functions. Over the next week and a half, we'll keep growing it. And it'll be several weeks as we grow. It's not going to be a huge list, but we should start with some very basic ones. All right, let's start with this first one. The derivative of 1 is 0. All right. Can we convince ourselves that that's true? Well, let's think about the function 1. What does the function 1 look like? Straight line, right? It's a constant. Now, when we think about derivative is saying what? What is derivative measuring? It's measuring slope. Another word? Our phrase? Rate of change. Slope's rate of change. How much does 1 change? It doesn't change at all. If you think about it in terms of slope, the slope of this line, turns out the tangent line, I guess I should draw the tangent line. So this is the function 1. Does anyone know what the tangent line to the function looks like? It looks like this. It's the same line. And it has slope 0. All right, so that one, that's pretty convincing. And that's a good enough argument for us. You can go to the limit definition. It's very simple. The next one says, suppose you have x to a power. So x to any power. Now, we're not going to prove x to any power today, but the rule is for x to any power, and we'll just say we're going to assume it's for x to any power. Then it says, okay, if you want to take the root of x to a power, the rule is the following. You find that power, n in this case, and you move it down. So notice that the n came down. And then the upstairs, you subtract 1. So bring the power down in front, subtract 1 from the power upstairs. And we'll go through why that works for some powers. Now, I want to make a comment here that we're going to encounter some functions from time to time. And so, for instance, you might see a function called square root. This is sort of an algebra way we think of this function. And we worked with it a lot. But it's not good for us because it doesn't mesh well with our rules. So what will we use instead of square root?
Power of 1/2.
Yes. This becomes x to the 1/2 power. So this is calculus. So when we're dealing with square root, we always say, let's switch it to x to the 1/2. Why do we switch? It comes down to saying it's how our rules are built. Our rules are built to handle x to a power. And so that's why we say, oh, I don't want to have that square root. I want to have x to a power. So write it as x to the 1/2. A couple of other things you might see. You might see something like, let's say, 4. What does that mean? Yeah, x to the 1/4. So this is the 4th root of x. You might see something like 1 over x squared. What will that become? X to the -2. So you want to be able to put things into the rule. So one of the things that we have to learn, this is a bit true in our class, it's really, really true next semester. Well, students in Calc 2, if you have any friends in Calc 2 that are stressing out right now, they have to master the art of putting things into very specific forms. And so a lot of what we have to learn in calculus is the art of writing things so our rules apply. So be able to handle powers of x in different ways. If you see square root symbols or nth root symbols, know how to turn that in. If you see things downstairs, know how to rewrite that. All right, our other function is e to the x. And, well, what can we say? It's a great function. The derivative of e to the x is e to the x. Wow, that's cool. Why is that? We'll explain that in a few minutes. Okay, so we've talked about why the derivative of 1 equals 0. Let's sort of sketch a proof for, say, x to a whole number. And so you don't need to write this part down, but we'll walk through it. So what can you do? So you have the derivative of x to the n. We'll just talk through it. So when we make the rules, the way we make the rules is that we go back to our limit definitions. And now, after we've defined the rules, we won't need to go back. So once we've figured out what happens with the derivative of x to the n in general, we'll never have to do that derivative the long way again. So this goes to an alternative definition of the derivative. So instead of having a limit as h goes to 0, you can have a limit as z goes to x. But it's one of our allowed forms. So we have f of z minus f of x over z minus x. Okay. Well, that becomes f of z. When I talk about f, this is our f of x. So that's z to the n minus x to the n over z minus x. Now, the claim is z to the n minus x to the n factors. And it factors as z minus x times stuff. So we can check that. Well, we can at least convince ourselves. Z times z to the n minus 1. What does that give us? Z times z to the power n minus 1. I have 1z. Here's n minus 1 z's. 1z.
Z to the n.
Oh, yes, it's z to the n. Good. Cool. Cool. And look, I need a z to the n. Nice. And now at this point, you're like, there's a lot more stuff, though, Steve. Yeah, it's okay. We haven't finished. Now, suppose we look at that one versus this one. What will this be? Be x times z to what power? N minus 1. What will happen if we multiply these together? You'll have an x, z, n minus 1. But one is being added and one is being subtracted. So what happens? They cancel. So those terms cancel. You're like, oh, well, that was very convenient. Did you mean that to happen? Yes. And then you can say, well, what if you try that again? Well, you get x squared z to the n minus 3 minus, x squared z to the n minus 2 minus x squared z to the n minus 2. Those cancel. In fact, everything cancels all the way down except the very first term, which was z to the n, and there'll be a very last term, which is this x times x to the n minus 1, which is x to the n. All right. Well, the great thing is you have a z minus x in front. That cancels with the z minus x downstairs. That gets rid of your 0 over 0. Woohoo! Now z goes to x, so you have a whole bunch of x to the n minus 1s. How many? You have n of them. And so you have n x to the power n minus 1. And we're done. That's the whole argument. Now, we will get it for general numbers. This is for whole positive numbers. All right, so that's x to the n. Now let's talk about e to the x. Does anybody remember where they saw e, or where you may have seen e talked about, say, when you were learning algebra early on? Sometimes it comes up in terms of money, compound interest. Have you ever, yes? All right. See, some people are like, yeah, I like the money. I'm an engineer. So one of the ways that you first see E is you have this notion like compounded continuously interest. And so you say, well, that relates to this expression 1 plus 1 over n to the n. And so you think of like, well, maybe it's like if you do it once a year versus 100 times a year versus 1,000,000 times a year versus constantly doing it. And it turns out that with constant, continuously compounded interest is what you get as you take n goes to infinity of this expression, and you end up with this really cool number, 2.71828. It's like the chant. Come on now, let's integrate. 2.71828. Wah! Forgot to bring my pom-poms, but all right. So, okay, so we have E has this form. Now, if you think about this for a second, say, well, let's make this inside part, this 1 over n, we're going to change this name to be h. So we're going to let h be 1 over n. So if n is big, h is small. So h equals 1 over n is small, and then this n is 1 over h. So you have E is about 1 plus h to the 1 over h. Raise both sides to the h power. E to the h is about 1 plus h. Or e to the h minus 1 is about h. Or e to the h minus 1 over h is about 1. Which is just a very long-winded way to come to the conclusion that, you know what? E has this really cool fact. If you take e to the power h, subtract 1, divide by h, take a limit as h goes to 0, you get 1. Now, how does that help us? Well, let's apply the rule. The derivative of e to the x, limit as h goes to 0 of definition, plug in x plus h into your function, so e to the power x plus h minus e to the x over h. Addition upstairs in your exponent becomes multiplication. So that's to say e to the x plus h is e to the x times e to the h. And then you look and say, oh, or perhaps you say, ah. But either way, you say, hey, there's a common term, so we can pull out that common term. And because that doesn't have anything to do with h, you can pull all the way out of the limit. So you have an e to the x on the outside, and a limit as h goes to 0 of e to the h minus 1 over h. And then we say, wait a second, that limit is 1. So this part here, this goes to 1. And so we end up with just the e to the x. All right. Now, the big takeaway from this is that when it comes to functions that we like, we really like e to the x. And so if you ever go and talk to some of students who, for instance, are taking differential equations, they say, oh yes, it's always e to the x, all day, every day. That's all we ever talk about. E to the x this, e to the x that. It's so cool because it has that wonderful property that when you take the derivative of e to the x, you get e to the x back. So we really, really like e to the x. All right. So those are our functions. Derivative of 1 is 0. Derivative of x to the n, and x to the power n minus 1. Derivative of e to the x, 0. All right, any questions about those 3 facts? Those are our building blocks for today. Okay. Well, now that we have rules for some basic building blocks, we should also have rules for combining functions. And this is putting things together. So let's talk about our very first rule. And this is one of our most important rules. We do it so often, we almost do it without thinking. And so our first rule says, suppose I take the derivative of some constant times f of x plus some constant times g of x. Well, I can break up over the addition, and I can pull the constants out. Now, there's a technical term for this called linear. Linear is a shorthand way in mathematics to say nice. But really, the punchline here is if I have addition, I can break my problem up. Unfortunately for us, it only works for addition upstairs. It doesn't work for addition downstairs. But that's why we take Calc 2. So, if I have addition, I can break things up. If I have constants, I can move constants outside of the derivative. So that's our first rule. Okay. So just break things into smaller pieces. All right. Well, with that in mind, let's do a problem. Find the derivative. This seems like a pretty simple function, the kind of function you'd see on your typical stroll around campus. Find the derivative. 6x to the power 10 minus x cubed plus the square root of x plus 5x squared plus x to the power e plus pi to the power 7 minus 11 e to the power x. All right, let's take some time now and think about what's going on. Now, your initial reaction when you see something like this might be like, ah, because there's a big thing here. Like, oh, it's a big thing. But do you see all these minuses and pluses? When you see minuses and pluses, it says, oh, I can break things into small things. So instead of thinking of it as one big thing, you can think of it as 7 small things as you work your way across. Now, you might say, that doesn't make me feel better. But the thing is, small problems are easy problems. So, do we have an answer? Anyone ready to read it out for us? All right, I see a hand here.
60x to the 9th minus 3x squared plus 1/2 x to the negative half minus 10x to the negative third plus ex to the e minus 1 plus 0 minus 11 e to the x.
Ah, wonderful. That's what I got. Now, you'll notice a couple of things we mentioned before. Learn to rewrite the square root and x downstairs. So this amount of notation is not what you're expected to do, but this is just to emphasize the process. So this will become an automatic thing. Now, most of these are not too surprising. Once you learn to rewrite the powers of x, most of these rules are pretty quick. What about this one? This seems a little bit off, doesn't it? X to the e. Why did we throw that in there? Right. Well, certainly, there's a suggestion like get used to the notation x to the n is n times x to the n minus 1. I will also tell you, we kind of put it in there to see if you're paying attention. Because people start to learn rules, but then they start to sort of get muddy with the rules. And they're like, oh, e to the x, that's e to the x. And like, okay, I got that rule down. And then you see something like x to the, it's like, oh yeah, that's just the derivative itself, right? No. Be careful. Be careful. We know how you think. So don't think that way. That's a strange statement. But just be careful. Just be careful. What about pi to the 7th? Shouldn't the 7 come down? 7 times pi to the 6? Why did it go away? Because it's a constant. Constants can be written in strange ways. So be open to saying, oh, that's just a constant. And I can just treat it like a constant. Even if it's written with lots of symbols, as long as it's a constant, I treat it like any other constant. I treat it like it was a 5. All right, good. Okay, so that's an example of our first rule, linear. And this is probably the most used rule, and we use it so often it'll become second nature. The next rule for today is suppose you have two functions multiplying together. So f of x and g of x, they're multiplying together. Well, the claim is that what you get is f prime of x, g of x, plus f of x, g prime of x. Now, that may not be your first instinct. Most people, when they say, hey, if I want to take the derivative of two functions multiplying, what seems to be the right thing to do? So if I take the derivative of f of x, g of x, a lot of people will say, oh, shouldn't this be f prime of x times g prime of x? Does it? No. With a little asterisk there, but I'll explain the asterisk at some point. But no. Let's convince ourselves. Let's take a very simple function for f of x and g of x. Suppose I take f of x to be x and g of x to be x. What is x times x? X squared. Do we know what the derivative of x squared is? 2x. Well, what's the derivative of just x? 1. So, does 2x equal 1 times 1? No. So this is not true. And in fact, it's basically never true, except in some very weird functions. So it's not the simple, obvious thing. But it turns out to not be that bad. Now, the way I like to think of the product rule is every function gets a turn. So I have two functions I'm multiplying together. And as they say, look, everybody wants to be a derivative. But we're going to let them do it one at a time. And say, okay, who's up first? And this function says, well, I'm in the first spot, so make me first. So I say, okay, you get to be the derivative this time. So f prime of x, g of x. Okay, who's next? My turn. I'm the g. Okay. Now in that case, the f stays as is, and we take the derivative of g. So it's f prime g of x plus f of x, g prime of x. Derivative of the first times the second plus the first times the derivative of the second. And there's various ways people remember it. Whatever you do to remember things, that's fine. Let's test your intuition. Suppose I asked you, what's the derivative of f of x times g of x times h of x? You had three things multiplying together. What would it be? Just based off of what we said about the derivative with the product rule. See, somewhat of a timid hand.
The prime of x times g of x plus the prime, or times, like...
So f prime of x
g of x times h of x.
Times g of x times h of x, okay. So f got its turn, plus?
The prime g of x times f of x times h of x.
Okay, so now g got its turn, yes?
Plus the prime of h of x times f of x.
And then h got its turn. And that's the correct answer. So if you have multiple things multiplying together, just remember everything gets its turn. And so here f got its turn, here g got its turn, here h got its turn, and then you add them all together. All right, good. Now how does the proof for the product rule work? We should see the proof. And again, this is not so important to know, but it's good to convince ourselves. So it's on the handout. So what do you do? Well, we say we go back to our rules. So the derivative of f of x, g of x. So we plug into our definition. You have f of x plus h, g of x plus h, minus f of x, g of x over h. And now we do something here. There's this part in a different color, more bluish type color here. If you stare at it for a second, what do you notice about this expression? It's 0, right? Because there's a minus and a plus. Cool. You are allowed to add 0. Adding 0 never changes anything. But you're probably thinking, but does it ever help anything? Well, the answer is yes, because we didn't just add 0. We had a very well chosen 0. This is the chosen 0. Now, why does it work so well? Well, essentially, the thing is that we're changing two things between the original part, right? F and G have x plus h both. Here they have both x. Now, notice, in this part, you're only changing only with the f term. And here, you're changing only with the g term. So now you're sort of putting an intermediate stepping stone. So that's what's going to help us win. So you say, okay, so now from the first part, you say, since this g of x plus h is the same, consistent, pull it out, you have f of x plus h minus f of x over h. Then on the last part, well, the f of x is consistent, pull it out, g of x plus h minus g of x over h. And now we say, good news, things are going to work out nicely, because this part becomes f prime, this part becomes g. This, well, that's f, that's super easy to see, and this is your g prime. And that's the way it works. There's sort of a visual way to think about it, and I don't know if this is going to help anybody, but I've always wanted to draw this picture. I've never gone to draw this picture before. So essentially what's going on here is when you have your f of x plus h, g of x plus h, well, you can think of you have f and you have g, and then you have a little bit of change in f. And that's how much f of x plus h is f plus a little bit, and g plus a little bit. And now, what are we doing? Well, we're basically trying to say, what's the area between the two triangles? Between the two rectangles. And if we stare at this, we say, well, we can think of it as three pieces. There's this piece right here, and how much area is in that piece? F change in G. And then there's this part on the side. What does that look like? Yeah, change in F times G. And then there's this little corner here, which is unimportant. Too small. So we say, well, look, if I want to find the change in F times G, it's the change in F times G plus F times the change in G plus something unimportant. And that's what that's saying. So that's sort of a visual way to think about it. All right, well, let's try out a quick problem involving the product rule. We'll just do this one together. Find the derivative of x to the 2/3 times e to the x. Okay, so how do I know this is a product rule problem? What about this problem says you should pull out your product rule? Because you have a product, right? See, the names are very suggestive. Oh, you have a product. How about you use the product rule? Ah, very clever. Cool. Okay. So, The one thing about e to the x with the product rule is you always get confused whether or not you took the derivative. So keep track of things. So you have our two pieces. You can call them f and g momentarily. And some people say, oh, first take the derivative of f times g. Some people say, take f times the derivative of g. As long as everybody gets its turn, life is good. Okay, so I'll start by saying take the derivative of the first term. What's the derivative of x to the 2/3 power? 2/3 x to the negative 1/3, right? Always subtract 1. 2/3 subtract 1 is minus 1/3. Now, times the function. We're not taking any derivatives. So just copy. Don't even think about it. Plus the function. Again, just copying. Now we have to think about what's the derivative of e to the x? E to the x. Okay, didn't have to think too hard. All right. And so we've succeeded. We factored. We took derivatives. Woohoo! Let's do a little bit of practice of cleaning things up. Suppose you want to clean this up. What do they have in common? They have e to the x. Okay. So in terms of derivative, we're done. Okay, so we're happy here. But we can go a little bit further. They both have e to the x. What else do they have in common?
X is to a certain amount cubed.
Okay, so they both have x's to a power. All right, so here's my question for you. Let's pull out a power of x. When we pull out powers of x, which power of x do we pull out? And why? We pull out the smaller one. That's fantastic. That is the correct answer. Which one's the smaller one? The negative 1/3, because minus 1/3 is smaller than positive 2/3. So yeah, you pull out the smaller power of x. X to the minus 1/3. All right. Pull out the common e to the x and the smaller power of x. What's left? In your first term, what do you have remaining after you pull out x to the negative 1/3 and e to the x? 2/3. Now, let's see if we've lived a good, clean algebra life. What's left here? X to what power?
Squared. No. Power 1.
X to the power 1. X to the 1. Now, you might be saying, what? How do you get the power of 1 there? Well, here's one way to think about it. You can think about it and say, okay, for what goes here, you say, what was it originally? Well, it was 2/3. Then subtract what you pulled out. Because we're removing that much. So when you subtract what you pull out. So minus a minus makes us 3/3, which is 1. Alternatively, you can say, oh, wait, what does this need to be? So x to what power times x to minus 1/3 will give me x to the 2/3. And the answer will be x to the power 1. So this is indeed x to the power 1. So you want to get comfortable with doing some of these algebraic manipulations here. Because these are things that you may see again. Yes, you may. All right, let's see. How are we doing on time? Well, we should probably move to our last set of rules, which are the reciprocal rule, but more generally the quotient rule. So the reciprocal rule is in some sense a special case of the quotient rule. But it's also the case that if you combine the product rule and the reciprocal rule together, the quotient rule follows automatically. So the quotient rule says, how do you handle a function divided by another function? And the answer is, there's a formula for it. Now, this one is a little bit tricky to remember. Not so much because of the downstairs, you just square the denominator. It's because there's a minus sign. And you gotta be very careful here because if you put the wrong sign in, you'll be off in your final answer. So you have to find a way to remember it. And I'd like to say that, well, after a while you just get used to it. But in all honesty, this morning I was recording some practice problems, and I messed it up 3 times in a row. Now, it won't look like it in the video, because I was like, oh, okay, let me go grab a new piece of paper. But however it helps. So I think some people, back when I was young, they'd say, oh, it's low D high minus high D low. I don't know if they still do that. I don't know what the cool things are that kids do these days to remember it. The thing is, if it helps you remember, it's not stupid. So just remember that. All right. So we're learning these rules, learning how things fit together. So now we can do more interesting questions. Something like this. The derivative of the square root of x plus x squared over 3x cubed plus e to the x. Now this is what I would call an example of an onion problem. And you're like, yes, there's going to be some tears, right? No, it's not because we're going to cry. It's because there's layers. Onions have layers. And these problems have layers. And so the thing is that this isn't just like one rule. This is many rules put together. For instance, what do you see? Just first glance. A quotient. So there's going to be a quotient rule. What's here? This x e to the x. Product rule. How about things like x to the n? Yeah, we have several of those. How about linear? Break up over addition? Yes. Can you pull out constants? Yes. Every rule we've talked about comes into play. Now the thing is, we can put rules together in lots of ways. You have to keep track of how the rules came together. And so, for instance, what's the outermost layer of our onion? What's the biggest rule? First rule you have to deal with. Quotient rule. So that's your big rule. All right. Now, the next rules, let's just pull out, is you have the linear rules when you have to deal with derivatives here. Because you have to break up over addition and subtraction. You have to deal with x to a power. Okay, and that shows up in several places. What else do we need to worry about? Product rule. And I should have also boxed the x. And then there's one other thing we didn't mention yet, which is you also have the e to the x that you have to take care of. So all these rules come into place. And so can we do this? And the answer is yes. And with practice, we can do it very quickly in about a minute. So here we go. Take the bottom. Low times the root of the top. By the way, square root of x, let's just remind ourselves, means x to 1/2. So that would be 1/2 x to minus 1/2. Root of x squared, 2x. Notice I'm not even thinking about the linear part. It just becomes automatic. So low d high minus high d low. What's the root of 3x cubed? 9x squared. Okay, root of x e to the x, okay. Root of the first is 1 times the second plus the first times the root of the second. So there was our product rule. All divide by 3x cubed plus x e to the x squared, like the bottom squared. Now, at this stage, what do you do? Well, you box your answer, because that's the derivative. And unless they tell you to simplify, you don't have to, because we're the nice calculus class. And, all right, normally this is where I say, good, wonderful time, lots of fun today. Here's a fun multiple choice problem. And then we look at it and say, oh, gosh, what could it be? But we don't have time. The answer was D. But anyways, you can take a look at it later on. All right, we'll pick up again next time.